Now let's have a look at a special Maclaurin series called the Binomial series. This is actually the Maclaurin series of 1 plus x to the power k, and the important point here is that the k is any real number. Now we already know what will happen if k is just a positive integer. For example, if k is equal to 2, we already know how to expand this one, right? That is 1 squared plus 2 times 1 times x plus x squared, right? If k is equal to 2. And if k is equal to 3, and likewise if they are positive integers, we can use that Pascal's triangle and get the expansion. But the interesting thing here is that when you find a certain Maclaurin series, I mean this Maclaurin series, then you can see we will get an expansion no matter whether k is a integer or not. Even for negative numbers we can get the expansion, and the difference is, now if k is a integer, a positive integer, you will get a finite number of terms in the expansion. But later you will see, if k is a fraction, if k is not an integer, then the expansion of this one will get an infinite number of terms. In fact, a Taylor series expanded at 0, and in that Taylor series you will get infinite number of terms. But when it is a positive integer, you will get only a finite number of terms. Okay, so let's try to figure out the Taylor series around 0, or in fact the Maclaurin series of this function by the basic principles, right? So we can see fx is equal to 1 plus x to the power k, and therefore f0 now we are trying to figure out this one, right? So in order to calculate cn, we will need the derivatives of f evaluated at 0, right? And the first numbers, f0 is equal to f to the power 0th derivative, and that is equal to just the original function. And f0, if you substitute 0 here, it will be 1. And f1, the first derivative of x will be equal to k times 1 plus x to the power k minus 1. Therefore, the first derivative evaluated at 0 will be k. When you substitute 0 here, you will get k. And how about the second derivative? Then you will get this number as the coefficient, and here you will get 1 plus x to the power k minus 2, and the value evaluated will be equal to k times k minus 1. Now see, if it is 1, you will have k minus 1. When it is 2, you will get k minus 2. So keep note on this pattern, right? And then f of 3, the third derivative will be, now you will need to have this one also as the as a coefficient. So k minus 1 times k minus 2, and the power will be k minus 3. Now see, here you have 3 and you have 3 here, and see when this is 3, you will have only 2 because the power of the previous term will come as a coefficient in the next step, right? Here you don't have 3, I mean k minus 3 terms. If it is 2, you have 1. If it is 3, you have 2, right? So be familiar with this pattern, so eventually we can write down the general term. So evaluated at this one will only give these three terms, k minus 1, k minus 2, right? So likewise, if we do the calculation, if we proceed like that, the nth derivative will be equal to k times k minus 1, k minus 2, and likewise it will go up to k minus n minus 1th step. See, this same pattern will continue, and the power you will get k minus n, right? So that's the same the same pattern that we continued up to the nth derivative. And here when you substitute 0, only these coefficients will remain, right? So when you substitute 0, you will have k times k minus 1, k minus 2 up to now by solving this bracket, you can even write it as k minus n plus 1. Okay, so what you will have is k minus n plus 1, right? Okay, now, and remember, this is true for any real number k. This need not to be a integer all the time. You can even have numbers like half, right? For k, you can even have numbers like half. It need not to be an integer like this, right? It is not necessary for these to be integers. Okay, so now we have figured out a certain pattern for the nth derivative of f evaluated at 0, right? So our Cn coefficient will follow this equation. That means the Cnth coefficient will be equal to Fn evaluated at 0, and that is k minus 1, k minus 2 up to k minus n plus 1, right? And divided by n factorial, right? So this will be our Cn coefficient. Therefore, the power series of this term 1 plus x to the power k will be equal to sigma n goes from 0 to infinity k minus this whole thing will come in this place, right? Because it is our Cn divided by n factorial x to the power n, right? So this is the Maclaurin series of the function 1 plus x to the power k, and this is called the binomial series, right? This is called the binomial series. Okay, and there are few more things that we need to discuss in the theory of binomial series. So first thing first, the radius of convergence in the power series. And to calculate radius, we will follow our same usual technique, that is through the ratio test. So when we calculate the nth coefficient and get the ratio, you can see that the limit of this ratio will be equal to the modulus of x. So from the theory of ratio tests, we can say that the series will converge for the values of x strictly less than 1, and diverge when the modulus is greater than 1. That is from the ratio test. And then how about the endpoints? Now the endpoints will depend, the convergence at the endpoints will depend on the value of k. Now this diagram does not represent the value of x, okay, because we already know that the series will only converge within this region of x, right? But we still don't know what will happen at the endpoints. Now the endpoints, the convergence of the endpoint will depend on k. That's what I want to mention within this diagram. So if the k value is greater than or equal to 0, so this represents the case greater than or equal to 0, then at both endpoints, both these endpoints, the above series will converge, right? We can prove that. And if the value of k is strictly greater than -1 and less than or equal to 0, then the series will only converge at the right hand endpoint, right? And it does not converge for x equals -1. And for the values of k less than or equal to -1, this is -1, so for the values less than or equal to -1, the series does not converge at least one, it does not converge at -1 as well as at +1. So now don't mix these two diagrams, right? This diagram represents the value of k and this diagram is for the value of x, and through the ratio test we already found the interval, and to determine the convergence at the endpoints we have this sort of a relationship, right? You have to at each of these categories you have to substitute the endpoint manually and see whether the series converges or not, and from in that way we can find these results, right? I did not do the computations, but this is how it goes, right? Okay, so now we discussed the radius of convergence in the binomial series, and the next thing is the notation for this coefficient. For this particular coefficient, the binomial coefficient, there is a special notation and it is represented like this. Now remember, this k can be any number, right? It need not to be a real integer all the time. So according to this this notation, we can rewrite our binomial expansion in this way, right? Instead of writing this whole big term, we can rewrite the notation of binomial coefficient like this. And let's say you should remember that this is not necessary to be an integer all the time. Say for example, we can even have numbers like k equals -12, right? We can have numbers like this, -12. So the coefficient will be like this, n x to the power n. So accordingly the terms in the series will change, right? So that then what we have is 1 plus k, where k is -12. So we have this one to the power x, and then we have -12 times -12 minus 1, which is negative 3 over 2, right, divided by 2 factorial x to the power 2. And then you will get negative half, negative 3 by 2, and then negative half minus 2 is equal to negative 5 over 2, right? And likewise it will keep on increasing, which will form a infinite summation, right? But just observe, when you have a integer, say for example, if k is equal to 2, right, if k is equal to 2, then once again you can write the binomial coefficient and the series expansion. But just see what will happen. Here you have 1 and here you have 2x, and here you will get 2 times 2 minus 1, 2 factorial x squared. And after that, in each and every binomial coefficient, you will get this k minus 2 term. So, as k is equal to 2 in this case, from here onwards, you will get 0. Hence, this will only give a finite number of terms, right? So, if k is a positive integer, it will only give a finite number of terms. And we already know this one. See, if you simplify this one, what you have is 2x plus x squared. And you already know this expansion by the Pascal's triangle, right? So, we don't even have to consider this as a Maclaurin series. So, the importance of this Maclaurin series or the binomial series will come into play when you have non-integer powers, right? So, what you have to remember is, even for a non-integer power, there is a certain expansion, and the coefficients of that expansion can be found from this relationship. And also, if this is a non-integer, you will get a summation of infinite terms, and if it is an integer, you will only have a finite number of terms. And there's one final thing that I would like to mention about this binomial expansion, that is, it is always not necessary to have a x term in the right, but you should have 1 in the left term as the left term, but it is not a must to have x here all the time. It's like, for example, what if we need to write the binomial expansion of 4 minus x, which is equal to 4 minus x to the power negative half. So, how are we going to do this one? Now, see, if it is 1 plus x to the power negative half, we have this expansion. But the thing is, now you have this one. So, first of all, in order to write the binomial expansion, you will need to convert this function into this required format. So, accordingly, we can have we can rewrite it like this, right? We can take 4 out, then you will get x over 4 everything to the power negative half, and that means you can distribute this negative power across the multiplication, and you will eventually get x minus 4 to the power negative half. And this one you can write it as 1 over 2, and here you will have 1 minus x over 4 to the power negative half. But still there is one more thing that you should do. See, here you have a 1 plus. Now don't mix this one with those initial power series expansion for this function. Okay, now this was written, this was a different result, and here you need a minus, right? But in the binomial expansion, we will need a plus in between these two terms, right? So here we need a plus sign in between. So we should rewrite this one once again so that you have a plus sign, but you cannot just delete this negative and write a plus instead, then we will be changing the original problem. So what we can do is we can rewrite it like this. Hence, now we have everything according to our binomial expansion theorem, right? So we can just consider this portion as 1 plus y to the power negative half. So the binomial expansion will be very similar, but instead of this x, you will get the required y term. I mean the whatever the term you have in the right hand side, which is separated by this negative sign. So what you will have is negative half times negative x over 4 plus negative half negative 3 over 2 factorial times negative x over 4 to the power 2, and likewise you can rewrite this one by replacing this term with negative x over 4. And then now we saw that for this binomial expansion, the radius of convergence was less than 1. I mean x value was less than 1, and we also saw that when k is greater than, k is greater than negative 1 and less than or equal to 0, we have only the right hand side endpoint. Okay, so anyway the radius will be equal to 1, and in this case, so here now in order to get the radius, what you need is the modulus of this right hand term, and in this case the modulus of the right hand term will represent the modulus of x by 4, right? Not just x. So this thing should be less than 1, therefore x will be less than 4, therefore the radius will be equal to 4, right? So putting all together, we can say that the power series or the Maclaurin series of this function will be like this, and it will converge at a radius of 4. That means from 0 to 4 in both sides. And by looking at this relationship, we can say that since in that case k is equal to negative half, it will only when we consider the endpoints, it will only converge for the right hand side endpoints. That means the interval of convergence will be from negative 4 open bracket, and it will converge for the right hand side endpoint. So that's all you need to know about the the binomial series, and it's very important that you have a good idea about this binomial expansion. Now, if I summarize what we did so far in this binomial series, first we calculated the expansion of 1 plus x to the power k, and from the Pascal's triangle we already knew that there is a certain expansion when the power is a positive number, positive integer. Like, we didn't know the expansion for things like this, okay? We only knew the expansion for things like this, right, from the Pascal's triangle. And for all the remaining numbers, for negative numbers as well as for these kinds of fractions, we need the binomial expansion. and the coefficients we were able to calculate it through these fundamental steps, and we saw a certain pattern and we were able to write it like that. And then we calculated the radius of convergence, and we saw that the radius was equal to 1, and these are the suitable x values. And the convergence of the endpoints will depend on the value of k, and we did not do a proof for this part, right? But there is a result like this, right? So for the endpoints, if k is greater than or equal to 0, it converges for both. If k is in this region, it will converge only for this one. If k is not within, if k is in this region, it for both endpoints the series will diverge. Therefore here the interval of convergence will be both open, and here left side open, right side close, and here both sides close, but you will have the same radius. Okay, right. And then we introduced a new notation for the coefficients, and this is called the binomial coefficient. And we can rewrite our binomial expansion like this, and we did 2 examples, and we saw that when k is a positive integer, the series terminates after a certain finite number. But when it is a fraction, no matter whether it is negative or positive, this series will keep on continuing, and it will have a infinite number of terms. And also we were able to find the Maclaurin series of a different type of a function by first rearranging it in this format. So for this format, there are 2 basic things that you should consider. First thing is you need to have 1 in the left hand term, and here it should be separated with a positive sign. So if they don't have these properties, you should be able to rearrange everything so that you have these properties, and thereafter you can apply the binomial expansion.